Now that we've looked at what the course is going to cover, the first thing we want to do is actually download the tool. So as you see here on my screen, I'm at wireshark.org. So you just go to www.wireshark.org. Over in this icon here, you click on download. Windows installer 64-bit. You can get multiple platforms, but in our case, we're just going to go ahead and use the Windows installer. So what we're going to do is once it downloads, we're just going to install the actual tool. So we go Tool, Downloads, and we double click Wireshark. Now, so you really need to install. You can read through this if you want, the license agreement. It's always nice to read through this, but unfortunately nobody really ever does. So click on I agree. And then you see this is what it's going to install, all these different things. Now T-Shark is a command line version of Wireshark. But for now, this is everything you need. And also this user guide is an excellent guide for doing actual Wireshark testing. It shows you how to do so many different things in Wireshark. So we just accept all the defaults. There's nothing here that we're going to actually change. And now this is the part where sometimes people get confused. Now it tells me I've currently got installed WinPCAP version 4.1.3. And it asks me, do I want to install in WinPCAP version 4.1.3? So since it shows that the WinPCAP version that I currently have installed is the same, I don't have to worry about installing it again, so I can just accept the fact that it's already installed and click Next. Now you might actually have to install WinPCAP if you never installed it before. And install USB cap, all those types of things. This is nothing we're going to do because we're not actually doing any USB cap traffic. So again, just accept the defaults and click Install. And that's pretty much the process of installing Wireshark. And now it will install. Once it gets done installing, you click Next, and we'll click Run Wireshark here just so we open. We close out of here. And that's all we want to do in this module. In this module, we went to the wireshark.org site, we downloaded the Wireshark utility, and we installed it. And now it's actually ready to go. Now in the next module, we're going to go and we'll go into this in more detail, and we'll look at some slides and explain this user interface that you're looking at now. And as you see here, it's already reading information from the wireless adapter on this computer. Again, Wireshark, once it's installed, it starts looking at your network traffic. That's a feature of the newer version. The older versions didn't do this. And that concludes what we wanted to do in this module. Again, next step in the section, we're going to actually do the interface. And we'll review how to use this user interface and what exactly you're looking at when you're looking at a Wireshark packet capture. Now we've installed Wireshark, the next thing we want to do is take a few minutes and talk about working with Wireshark, mainly the user interface. This is how you're going to interface with the program and actually interact with network traffic. So what we're going to do is we're going to explore this Wireshark interface. We're going to look at the different components of it and how you can access different things to analyze your network traffic. We're going to start with a packet capture. This is going to be our actual static file that we're going to present to you. And that static file is going to allow you to look at different network traffic and learn how to analyze that packet capture. Then we're going to examine the window sections. There's 3 main window sections of Wireshark. You're going to learn each one of those window sections and ways you can do to enhance your analysis of the network packets that you capture on the wire. We're going to identify some resources to assist. That is, where can we go from here? So we have more material in the course, but also places you can go and learn more information about this wonderful tool. So this is the actual Wireshark interface. So when you have a look here, you see we've got Welcome to Wireshark, and under there you have these network adapters. So as you look at this image here, you see these network adapters. The wireless network connection actually has a graph on it. That shows you that the wireless network connection is currently capturing packets on the network. And all we have to do is double click that or click on capture and start our capture, and we'll be able to actually identify that. So we have 2 methods to start our packet capture. We can use the menu, capture, select options, select start, or you can just double click the network adapter of your choice. My preference is to use the capture, the options, and the start. And this is actually what comes up when you use capture, options, and start. As you see here, we have all our interfaces. I have the wireless network connection selected here. And what we do is we just click on start. Once we click on Start, we'll start capturing packets. Let's take a look at it. So there's three main sections of the windows. We have the packet list. As you see here in the image, this packet list is showing you the source of the packet, the destination of the packet. So it starts in the far left corner with the number, and then self-explanatory, the number of the packet in the trace. And then it has the time, number of seconds ticked off between the packets, the source, in this case we have a Netgear source, and then this destination is the broadcast address. So in this case it's going to our network broadcast address. And this is address resolution protocol, which is just basically asking who has this address, tell me. And we'll look at that more details as we expand and learn more about TCP IP and how to conduct analysis of TCP IP traffic. Now in the packet details, which is located in the middle window, this is where we get into the actual frame. So as you see here on the actual image, we have the frame. Encapsulated inside that frame is Ethernet traffic. And inside the Ethernet traffic, we have address resolution protocol. This middle window is where you expand and be able to look at and view additional details of the packet, a thing that we call the header, which we'll learn more about as we continue and build your skill set. The next one is packet bytes. This is in the bottommost window, and as it says, this is the bytes. It's usually represented in hexadecimal, so it's easier to look at than binary bits of ones and zeros. So as you look at this, we see this packet bytes has these Fs. Those six sets of Fs means broadcast address. So now we're just looking at the broadcast address in the actual packet header itself. Now what you see here in the bytes is the destination comes before the source. That's something we'll have to look at as we get more and more detail of how to do packet analysis. So how about some resources for you? Wireshark User Guide is an excellent resource. This is where you can go, you can get information about Wireshark, and it has detailed information on how to use the Wireshark tool, including sample packet capture references. You have the wiki. So if you go to wireshark.org and you select the wiki, that's an excellent source and a resource for you to follow. SharkFest is this annual Wireshark conference that has all these great presentations and conference talks and workshops on how to use Wireshark in even more detail. So again, all these will help you learn more about the Wireshark tool. As we said, resources and references will help you become a Wireshark expert. So what we cover in this brief section of our module, we looked at the user interface for Wireshark. That is, we saw there was two main ways to start our packet capture. We could double-click the interface, or we could do it from the menu option. We also explored how to start a packet capture. This is, once I start a packet capture, what do I have to look at? Examine the window sections. We have three main sections within the Wireshark interface. We looked at each one of those. We had the packet information, the packet details, the packet bytes, and more information that we'll look at as we get more and more deeper into our information tutorial. And we identified some resources to learn more. We talked about the excellent Wireshark user guide. We talked about the concepts of how you could go to the wiki and you could actually research information on the wiki. And finally, we discussed the excellent resource and reference of SharkFest. Maybe you want to attend a SharkFest, or go just look at the information at the SharkFest site and read about the conference talks and presentations that are presented there by some of the top tier talent within the Wireshark community. So now that we've done this, the next thing we're going to do is apply our skills. We're going to apply the skills we just learned and actually use Wireshark to analyze our first packet capture. Next, we're going to examine your first packet capture. We're going to use this excellent reference we've already looked at of how to actually start up Wireshark. We're going to start up a static packet capture file, and you're going to learn how to use these three main sections of the Wireshark interface to analyze and get additional information on Wireshark as we look at network traffic and analysis of that traffic. And this concludes this section. In this exercise, what we're going to do is we're going to look at another capture file. And this is file1v2.pcap, and this is on a newer version of Wireshark. So we're looking at now version 3.2.4, and that's why we've shot the new video. So when you open this, the first thing you see is you see all this ARP traffic. All right, this ARP traffic is not normal. When you see ARP traffic like this, and you'll learn more about this as we progress through the course, and it's sequential. See how it's counting sequentially? So since it's counting sequentially, what that means is this is actually reconnaissance. So this is an example of somebody doing recon, but we'll learn more about that later. But now if we select one of these ARP packets, look over here. It goes the frame, it goes Ethernet, and then it goes ARP. So Address Resolution Protocol takes an IP address and gives us the physical MAC address. And when you see here, it's not part of IP. This is not encapsulated inside of IP. Everything you looked at thus far has been encapsulated inside of IP. So when you expand ARP, this is what it looks like. Of course, the MAC address for the sender, and then the broadcast is all Fs, or 255.255.255.255. So that's kind of how ARP looks, Address Resolution Protocol. As I said, this is recon, but you'll learn more about that later. So now, since ARP's not encapsulated inside of IP, let's look at UDP. So now when we enter UDP here in the filter, this is interesting. We got UDP here, but look what happens here. We have UDP going into a port, and what is the results? An ICMP packet. So what is going on here? Well, I'll pull this up for you. What this means is ICMP is used when the protocol doesn't have a mechanism to give you a message. In this case, it's giving you the message that the actual port is closed. How do we know that? Because right here, see how we've got our IP, we've got our ICMP's the encapsulated protocol, and we see destination unreachable, which is a type 3, and then the code is why it's unreachable. And we see here it's destination unreachable, port unreachable, but the key is, look at this. We have UDP encapsulated inside of IP. So that's how when the ICMP message gets back, the encapsulated protocol identifies what port was closed, in this case 40599. This is how we use ICMP by encapsulating UDP inside of it to give us a message that in this case the port is closed. All right, the last thing we want to look at here is our TCP. And we've already covered TCP some. We're not going to cover it much here. We just want to look at right here. We got a SYN, we got a SYNAC, which means in this case the destination port is 25, and SYNAC means port 25 is open. But when you start looking down here and you see all this red, this is again indications of recon. In this case, this is a port scan recon. Of course, these are things you'll learn about as you progress through the course. And we just wanted to show you another file in the latest version of Wireshark and update the actual content in this section. And we'll conclude the session here. Thank you. We review what takes place when you communicate within a network. So what we're going to cover in this section is we're going to categorize the client-to-server communication. That is, how do clients and servers communicate at the network level? Once we've done this, we're going to look at the domain name server. Domain name server takes the human readable form and prepares it for the machine. Then we're going to look at the address resolution protocol. This is how we take our information and we apply it within the network. So client-server communication. Clients use ports greater than 1023 in most cases. We consider these transient in nature, and this is because as clients, we do not spend much time in a connection. Therefore, it's transient, or another name for that is ephemeral. Think about how when you connect to a page on the internet, how much time do you spend before you click on something else? That's why we traditionally use client-side traffic as transient or ephemeral. Servers typically operate in the lower than the 1023 port range. This is what we call reserved or privileged ports. That's because you used to have reserved privileged permissions to be able to access them. So what this does is it's an open state and it just waits for connections. That is, it's a door that's open on the machine. This makes it much easier for an attacker, since they know the server is there to serve up services. That means it's always going to be there and available for an attacker. That's why most of the time the majority of the attacks are against servers, or as you'll learn nowadays against mobile devices because people use them like a computer. So the domain name server, when you type in that name, it maps that name to an IP address. This is because the computer wants to draw the raw data of binary ones and zeros. It does not care what the actual readable name is or if a human can read it or not. Remember, all computers do everything in binary. They want that IP address in ones and zeros. This is the language of the machine. Everything is in binary. To it, it doesn't matter what it looks like other than ones and zeros. Traditional IP address we see is represented by 4 decimal numbers. This is what we call dotted octet. That's because it's 8 bits of binary for each number. This example here we show is how humans typically view an address. It's 192.168.0.128. That's what it looks like to a human. This is what it looks like to the computer. This is 8 bits of binary for each number. As you see, the computer doesn't care about if we can read it or not. So when you look at those binary numbers, the ones and the zeros, it makes it a challenge to read. So for our purposes, we like to use hexadecimal representation of this. And this is the IP address in hexadecimal. That is, it's C0880080. This is how, when we start doing our protocol analysis, we want you to look at it. We want you to always look at things as if it's in hexadecimal, which moreover is binary, but we're not going to task you with trying to learn all those ones and zeros. It's much easier to look at 2 digits in hexadecimal, which represents 8 digits in binary. So this is easier. Some might be saying it is not, but trust us, once you practice, you'll be able to convert between the decimal and the hexadecimal as easy as writing your name. Now we come to address resolution protocol. Now, address resolution protocol is how we map the actual IP address. This is the main protocol for getting the data into the machine. The IP address just gets the data to the network. That is, it gets it to the data or the wide area network device, usually in the form of a router, that belongs to that local subnet. We need the MAC or the physical address to send the data into the machine. And this is how we use ARP. The address resolution protocol gives us that physical address to send the data into the machine. In this section, we've defined client-server communication. That is how clients and servers communicate. We have explored DNS and how it maps the name to an IP address. Remember, computers only care about binary, ones and zeros. They don't care about the numbers or in a human readable form. We enhanced our skills with information on ARP, the address resolution protocol. Remember, ARP is what we use to get us the physical address. And the physical address, or that MAC, that media access control address, that is the required address to get the data to the machine. Next up, we will explore these protocols and you'll get to look at the file 1 static packet capture file. Now we've discussed the theory for client and server communication. We will now apply our knowledge and skill to the static capture file that we've created, file 1 pcap.ng. You can open the file to follow along and complete the steps as I do, or you can watch first and then do it when you watch it again. So we just click on File, Open, and we find our file 1 pcap.ng. So once we open it, it will open up, and you see here we start off with packets, and on the left column you have the numbers, and then we've got all this ARP traffic. But before we get into that, what we want to do, we want to look at our DNS. Remember, DNS, domain name server, takes our name and converts it from human readable form to machine readable form, which of course is binary. So what we want to do is we want to go down here to where we find some DNS traffic, and we'll go through this several times, so you'll get to look at it quite often. So, and we'll show you quicker ways to do this. For now, we're learning the basics. So what we're going to do is we're going to look for a specific packet because I've researched this trace already. So now I come down here, and here's the packet I want, this 1093. So as you see here, we have www.udemy.com. That's the DNS query for the Udemy website. And in the middle window, you see here we have a source port which is greater than 1023. And we have a destination port which is 53, which is what the domain name server or DNS resides on. This points to the fact that clients normally use a port greater than 1023 and the service is less than 1023. Next thing we want to look at is the DNS information itself. So we click to expand this section that is called the domain system query. And in the query, it has a question. And that question is exactly what you probably think that question is. It's www.udemy.com. So when we look at this question, we see www.udemy.com. That's the question going to the server. So what we want to do is we're going to actually look at the actual query. We have that, and we got what's called type A for address record and classes and internet record. So now that we've looked at the query, what do you think we want to look for next? The response. So it's the very next packet, which makes it easy. So now when we look at the response, we see that the only difference is located at the bottom. There's the query, but in the response, we have this answer. And the answer comes out and gives us www.udemy.com is at this IP address. You can see here this 151.101.24.175. That is the IP address of the Udemy server. So now that we have that, that is actually replaced in our browser transparently to us, but it's replaced in our browser, and now it goes out and connects on that IP address to the server that's located there. Okay? Remember, the IP address is what the machine needs to get it to the correct location. So we return to our top window. We see right after the response, which created the machine readable form, we go into a series of connections to this port 80. Now we'll discuss what that is in the future, but right now, just understand that's a request to that web server to talk to me. And that's really what the main thing is. So now that we have this, we want to look at an example of ARP, the Address Resolution Protocol. Now ARP is local, so we'll not see the ARP for the Udemy server, but we have a number of ARP packets we can review. If we in our file locate packet number 3708, so we come down here, we'll page down, and we look for packet 3708. Again, we'll teach you a quicker way of doing this once we build your skill set. But right now, we're looking right there. And we see in packet 3708, the source MAC address is coming from a machine, and the destination address is representative of all these Fs. These Fs are the broadcast address. And you see, it's basically a question. Who has 192.168.0.7? Tell me. 192.168.0.1. So once you see this, you know that packet 3708 is the request. Well, where's the response? The response is here at packet number 3714. As you can see here, 192.168.0.7 is at MAC address in the hexadecimal again, CC3D821E514F. Now we have the physical address, and now that machine can receive data. This is the information for the packet ARP. So if we click on this, as you can see, the middle window now has Address Resolution Protocol. And if you look here, there's the MAC address. So now it tells you the IP address and the target MAC address. Now we have all this information that we've analyzed just in a couple of simple clicks of and looking in the tool Wireshark. As we said, it's much easier to represent the IP address in hexadecimal because we go here, there is the target IP address in numbers, but rather than looking at it in binary, we have it here C0A80001. In this section, you have verified how client and a server communicates and how DNS and ARP network traffic look like in Wireshark. One important thing to note here is that the entire process we have discussed, ARP and DNS by default and in accordance with the protocol, do not have any authentication. So the source of the packet is trusted to be whom they say they are. This is one of the biggest reasons we have all the attacks and all the hacks and the things you hear about in the news today continues to be that the protocols all are based on what's called the principle of trust. Now, the newer ones that we started to add to and stuff like that is changing that. But the hackers today still can use this principle of trust to their advantage when they conduct their attacks. Next up, we will look at your first protocols. And this concludes our introduction into client-server communication analysis. Me if you'd like to. And the first place we want to go is to packet number 1093. The easy way to do it. In this example, we're going to look at file1.pcapng. So once you open the file, you can follow along with me if you'd like to. And the first place we want to go is to packet number 1093. The easy way to do that is click on go to packet. And then you just put in the packet number you want to go to. And we wanted to go there because, yes, it's UDP, but moreover, it's DNS. And DNS happens all the time on the network. So when you look over here, you got your frame, you got your Ethernet, you got your IP encapsulated here in the middle window. That's where I'm at now. And then you got UDP, and then encapsulated inside of UDP is DNS. And you see this with the domain name system. In this case, it's a query. Now, Wireshark today will tell you it's a response. So one of the reasons for updating the actual videos is because Wireshark continues to add a lot of features that helps us out. And remember, the query is actually what they're looking for. So if we expand this query, we see this is udemy.com, and it's an address record in the class. IN stands for internet. So now let's go look at the response. Well, the response is right here in the 1094. So when you look at the response, it's the same thing, but it's the answer. And you see udemy.com, see other information and information about the actual packets itself. So the answers are giving us the answer we want, but we only ask for one IP address. So this is where we can get into problems, and attacks have been used because in the answer, what happens if I put an answer in there not even related to udemy.com and put in an answer there for a bank or something like that? Now in the modern day, as you see here, we got the SSL and Fastly LB. So these are just examples you see when people use the protocol for DNS. And in the old days, when you would query DNS, the biggest thing you were looking for with DNS was to limit the number of queries. So the more queries you did, the more problems you would have. So now we want to do, we've already looked at ARP, so we won't look at ARP again here. But what we will do is, let's look in the hexadecimal portion of the packet. So always remember this bottom window is the hexadecimal. Now it's actually in binary, but we don't want to represent it in binary because it can be a challenge to do that. But you see here, the information here is printable. So this bottom window represents the printable information within the packet. So that's what you want to be aware of when you're doing your analysis. So the one thing we'll think about here before we close up is all of this is a client-server relationship. And the client-server relationship exists today regardless if you're on a tablet, if you're on your phone, whatever device you're on, it's a client-server relationship. Traditionally, client ports, again, are above 1023, otherwise called ephemeral, and then server ports are usually below 1023 and called privileged. So we'll get into some of this as we continue to progress through the exercises. Next up, we'll continue on the theory of the protocol that makes the internet go, and of course, that's TCP IP. And we'll conclude the session here. Thank you. In this section, we will explore the main protocols that you will encounter on the network. We will explore the protocols in the following order: ICMP, UDP, followed by the dominant protocol, TCP. Once we've done this, we'll look at how these characteristics work in Wireshark. So ICMP, Internet Control Message Protocol. This is the protocol to communicate messages within the network. Some of the protocols do not have the capability to acknowledge and subsequently provide reliability, so they use ICMP. The most common form of ICMP is probably ping. This is the same ping that's used in sonar, and that is sending out a transmit request and waiting a return from a receiving target. Within our networks, we use two components. That is an echo request and an echo reply. This achieves the successful ping. So what that is just like sonar, we send out into our network a transmission and we look for a return. If we get the return, our network is reachable. Despite most being aware of the ping type of ICMP, there are many different types of ICMP. This is so it can provide messages for those protocols that require assistance. The ICMP type 3, also known as destination unreachable, it's very important because it lets us know if something is unreachable. This can show a multitude of different reasons for the destination being unreachable. How do we know which reason it is? There is a subtype called a code. This code will tell us why it's unreachable. One of the most common one that we will encounter is type 3 destination unreachable code 3. This means the reason it's unreachable is the port's unreachable. We also have type 3 code 13. Code 13 means the packet is administratively prohibited. So as you can see, these types, and especially the code types, can assist us in troubleshooting our network. And more importantly, knowing that in the case of identifying information for a security test or those types of things, a filter in place, if we send out an ICMP request and get back a type 3 code 13, that means we have some type of filter or a network router with an access control list in our path. The next protocol is UDP, User Datagram Protocol. As you may recall, it's a connectionless protocol. That is, it's not reliable and there's no guarantee of delivery. And that's the way it was designed. The best analogy for this is the mail system. When you mail a letter, there's no guarantee of a delivery. We take it, put it into the postal box or at the post office, and we rely on somebody else to deliver it. This is the same thing we do with UDP. Primarily use UDP for speed. And now we have TCP, Transmission Control Protocol. The main protocol for most of our network traffic we will analyze is that of TCP. This is because TCP is primarily used in majority of the different protocols. It provides us that reliability that we need for network communications that require it. Remember, we have the guarantee of delivery. We get this guarantee of delivery by an acknowledge capability. That is, when the data goes out, we receive an acknowledgement that the data was received. Once we receive that acknowledgement, we continue on with the data. As you can imagine, this requires additional overhead, so TCP can be used for guaranteed delivery. This overhead, of course, comes at a cost, and that cost is speed. That's why UDP is used for our streaming protocols. TCP also allows for transmission from both sides of the connection. That is, it's full duplex. The data is transmitted as a stream of data since the connection-oriented sets this up for us. Remember, we establish connection because we have the acknowledge capability. We transmit as a stream of data, and we'll learn more what this means as we look at it in Wireshark. In this section, we have taken a look at the workhorse protocol, ICMP. We've looked at the connectionless protocol of UDP. Remember, UDP, no guarantee of delivery, like our mail system. We closed out the session by briefly looking at the reliable and connection-oriented protocol, a TCP. Remember, TCP primarily is what we're going to use when it comes to the majority of our analysis. Most of the traffic will be under TCP protocol. Next, we will explore these protocols, applying our skills we've learned in the tool Wireshark. Now that we've reviewed some of the network protocols, we're going to apply our knowledge and skill to this static packet capture file, file1.pcap.ng. You can open the file again if you want to follow along and complete the steps as I do. So it's pretty easy to do, and once you've used it, Wireshark keeps it here in a history. So we just open up the file. Now, the packet we first want to work with is 8217, so 8,217. Now, that's a little bit far down into the trace. But a shortcut is just click into the capture here at the top window, hit Control and then the End key, and that takes you all the way to the bottom of the packet capture. Now, if you look here, we see packet 8217 right here. And over here to the right, you see echo ping request. and then it's immediately followed by packet 8218 echo ping reply. And what that tells us is that's our ping. So a request is went out from this host 192.168.0.7 out to that IP address. And that IP address you might recognize. This IP address is the IP address of the Udemy web server. So now we come down here and we look at the middle window. So if I expand the ICMP, you see, in fact, ICMP echo request is actually type 8. And if we go look at ICMP echo reply, it's type 0. So that's what I was talking about, how we've actually got the capability with ICMP to reflect a lot of different things. So now that we've explored ping, let us look at one more type of ICMP. Remember we said that some protocols use ICMP to notify the network about a communication status. We mentioned one of the more common ones being ICMP type 3 destination unreachable. So if we go to packet 1241 here, and I'll just control home to get to the top again, and then scroll down here to 1241. Again, we'll teach you a quicker way here soon. And that in black is highlighted. So when we look at packet 1241, we see this is an ICMP 3, right? ICMP type 3. So if we scroll to packet 1241, we see that this is an ICMP type 3, destination unreachable, and a code 3. And right here is both of these. We can see it in the top window, but in the middle window it shows it to us as well. We have a type 3, destination unreachable, and a code 3, which means it's an actual destination unreachable, port unreachable. Well, what's that little trick that we were saying we were going to teach you? It's time to teach you that now. So anytime you need to get to a specific packet, as we're reviewing here and building our packet captures, looking at static packet capture files, just click go to packet. And then you put in the packet number. So when I put in packet 1241, it goes to packet 1241 and highlights it. So that makes it a little bit easier to do our protocol analysis. So 1240 is the actual request, which was a DNS, domain name server query. So as you see, this was a Udemy request, but it was responded to with an ICMP type 3 destination unreachable and a code 3. Why? Because this request went to port 53. Remember, that's a door on the machine, and that door was not open. Right? So when you look at this packet 1240, we know that this was a DNS query and it uses UDP. So if we go in here now to look at some UDP traffic, so we click on the 1240 packet, there's UDP, and then we look inside the UDP portion of the packet. So as you see here, this query actually comes back with a response, 53, right there, in the destination port, right, in the domain name system response. So again, we're identifying domain name server information, and there's the answers and the queries and additional information here that you can explore and learn more. Remember, the most important thing we want is to identify what took place on the network. And in this case, it was a DNS query and a response of the DNS information, right? So this is a query response. And this here is a destination port unreachable, which means we tried to go to a port in this case, and it was not available. It was not open. So that's UDP. As you see, there's not a whole lot of packet details in the UDP packet. Remember, that is because it's connectionless and doesn't guarantee our delivery. Now let's look at some TCP communication. So now let's go to this packet 1239, which is TCP right here. All right, so when we look at it, this is an actual packet that's using protocol TCP. So if we expand it here and we scroll down to the flags, we see it has this ACK flag set. All right, so that allows for that reliability and guarantee of delivery. We're not going to spend too much time on this here because we'll explore it in great detail throughout the course. Remember, the more we get skills and the more knowledge and information we cover, we'll continue to build our skills to a more defined and process-based level. That is, we're going to learn how to analyze this and determine what takes place, in this case with TCP. As we said, TCP is our dominant protocol, and we'll actually have that in quite a few of our examples. So now let's look at the packet details. So now if we expand to TCP, we looked at the flags, and now we're going to expand the flags. These flags, as we'll learn in future exercises, are the control bits of the communications of TCP. This is how TCP has that guarantee of delivery and reliability. So we'll stop here and continue on with another section. Next up, we'll continue with building the TCP IP skills foundation, and that will be in the next module. In this section, we will explore the foundation of TCP/IP. That will include a review of the headers and the concept of encapsulation and how it looks on the network. We will learn about the network protocols. Following this, we will examine the encapsulation process and what it means on the network. Then we will close out this section with a brief exploration of the headers of the different protocols. The Internet was built with an openness and trust. Part of this was the creation of protocols for communication. These protocols were when the Internet was very small and there was no need for protection. So this led to the protocols being developed with this sense of trust. Then today, more than 40 years later, we are still running these same trusted protocols. Therein lies the problem and why there are so many attacks today. These protocols were not made for a network of the size that we have today. There is a requirement to provide information to the network at each layer of the communication. This is in the form of a header. This identifies the data to the receiver, and it's essential that we understand these headers. They are the key to what's taking place within the packet. Within the network, we have this process of wrapping the information within things, encapsulation. Everything within our network is encapsulated. Each layer has its own specific function for each header for this. This is an example of the OSI model in encapsulation. So as you can see here, each layer has an associated header that identifies what's taking place. This continues until we get to the physical layer, which is our binary ones and zeros. Encapsulation. We now want to look at this in our tool Wireshark. As this image shows, we have the data all encapsulated within the frame. This is followed by the Ethernet, and then the IP, followed by the encapsulated protocol, which in this example is UDP. This shows us how the network protocols are contained within one another. In this image, we're looking how the data flows between machines, and more importantly, between the layers of the network model, both logically and physically. Physically down the stack and then up the stack from the sender to the receiver. At each layer logically, the same function is taking place within the sender and the receiver. This is the IP header. This image shows the IPv4 header. And what we want to look at here is this, the protocol field. This is where that encapsulated protocol is identified. This image shows the UDP header, and as you can see, the header is very simple. Again, this is because it's connectionless and does not require any method to provide reliability. So it can be simple, as you see here. We have the source port and the destination port. This identifies the data to the service that receives it. This image, we have the TCP header, and this has quite a bit of data within. That's because we have to maintain that guarantee and that reliable service. We will not review all the information here. For now, we will look at the fact that it has the same important information as that of the source port and the destination port, so it identifies the service to and from. It also has these two fields for sequence and acknowledgement number. This allows for the connection-oriented requirement. Finally, within this header, you see these here. These are the flags or control bits of TCP. And each one of these identify additional details about the packet. In this section, we have explored network protocols. We explained and showed examples in the encapsulation process. We closed out the section with a brief look at the headers of the different protocols. Next, we will explore the information with a static packet capture file within the Wireshark tool.